Agent, long time no see. You have been selected for a high priority operation. Your mission is to complete Task 1, Target Detection and Identification. Failure is not an option. Do not disappoint me.
To achieve accurate navigation, our robot uses different control methods for straight movement and turning. Two DC motors are controlled using PWM, while a PID controller corrects errors to maintain smooth and accurate movement. The servo motor controls the steering angle using PWM signals from the SEM2. For turning, the robot uses a gyroscope to measure angular velocity. We integrate this over time to compute the yaw angle. The robot turns until the yaw reaches the target value for precise control. However, knowing how to move is not enough. The robot also needs to know where to go. The SEM32 communicates via UART at the 115200 baud, receiving movement commands and sending acknowledgements. This allows the robot to execute the movement algorithm step by step. For task 1, we ensure that the robot follows the algorithm accurately from left to right. We began with a single block test before scaling to more complex path.
Our objective is to enable a robot, Agent R1, to accurately identify obstacles in real time while navigating a grid. And we uses an R54, high camera, YOLO via instant segmentation, and a Flux server. We started with 5,000 images and expanded to 6250 images to fix straight miss detections like confusing SEM2 by weighing angles, distances, and lightning. We applied dynamic saturation, 50% grayscale conversion, and simulated motion blur up to 0.9 pixels to improve model generalization.
We achieved a highly accurate MDP 15 score of 0.891 and reached an inference speed of 12 milliseconds per frame, exceeding the 17 FPS threshold needed for real-time tasks. The system reduces false positives and handles mechanic misalignment by selecting frames with the largest overlap, prioritizing bigger bounding box and applying a strip over 0.85 confidence threshold. A multi-threaded Flux server ensures block-free communication across the system. Video streams via socket to a PC, UI data goes to an Android tablet via Bluetooth SPP, and movement instructions goes to the SD board via the USB serial.
Agent R1 is now connected to mission control. At the core of this link is our robust Bluetooth communication system. Operators can scan and select devices, establishing a fast and reliable connection. Once connected, the system enables bidirectional communication, sending commands and receiving real-time updates. Even under disruption, the system remains stable. If the connection is lost, the tablet continues listening and waits for a reconnection request from the robot.
With communication established, the Android interface becomes the mission control center. The GUI features a real-time grid-based arena visualizing the robot and its environment. Users can position obstacles, defining their location through drag and drop and their face direction by tapping on the obstacle in the grid. We have added features such as undo, redo, reset, and value clearing to support rapid testing and iteration. After configuring the obstacles, users can send the obstacle information by clicking Send Obstacles. The interface also displays the robot status, and the users can control the robot's movement by clicking the directional arrows. The system continuously updates the robot's position, obstacle values, and object positions upon receiving data from the robot. Additionally, operators can initiate Task 1 and Task 2 by clicking the corresponding buttons, executing the mission with precision.
Every mission needs a brain. As the algorithm team, our job was to build the intelligence behind Agent R1. We implemented a navigation algorithm using A-star search to help the robot analyze its surroundings and determine the best movement path.
To make the system reliable, we tuned key parameters such as obstacle distance threshold, turning angle, and reward values. These controlled how the robot evaluated paths, responded to obstacles, and adapted to changes in the environment.
In simulation, we tested how the algorithm behaved under different scenarios, verifying the Agent R1 could navigate efficiently and make consistent decisions before deployment.
During real-world testing, the mission didn't always go to plan. The robot could hesitate or make ineffective movements when conditions change, so we refined the algorithm to make it more adaptive, efficient, and reliable in real time.
In the end, we transformed law sensor into calculated, mission-ready decisions.
To survive in unknown terrain for Task 2, Agent R1 must constantly monitor its surroundings using its various onboard sensors, which provides real-time situational awareness. Firstly, the ultrasonic sensor, which acts as the robot's long-range radar, scanning the path ahead and detecting obstacles before collision. And second is the two IR sensor, both on the left and right, which provide short-range proximity and allowing the robot to circle around the obstacle without colliding. The robot drives forward while the ultrasonic sensor continuously pulls the obstacles ahead, and the encoders track the distance covered, which will be later used for the written path. When the obstacle is detected, the robot brakes and reports its distance traveled to the RPI and triggers the image capture. The RPI camera identifies the arrow direction and will send the appropriate command over UART. The SEM2 then executes a multi-step avoidance sequence using the side-mounted IR sensor to detect when it's cleared the obstacle's edge. And after avoiding both obstacles, it drives back based on the target distance it has recorded back to the parking space.